Hello friends, I am Zeki. Today I will make a presentation about internal memory. Let's begin with the basic concept of memory in a computer system. Memory is the part of system where data and instructions are stored. We can think of it as a short-term memory of the CPU. It enables fast data access much faster than external storage devices like hard drives. Computer memory exhibits different types of techniques, organizations, performance, size and cost. But no technology is optimal in memory requirements for a computer system. As a result, a computer equipped with a hierarchy of memory subsystems. We usually divide memory into two main categories: internal memory and external memory. Internal memory is directly connected to the CPU and plays a key role in performance, while external memory is used for long-term, large-capacity storage. Here we can see the distinction more clearly. Internal memory includes components like RAM, cache, and ROM. It's fast, volatile, and located inside the system. External memory, on the other hand, includes devices like hard drives, SSDs, or USB sticks. Internal memory provides temporary and rapid access, while external memory focuses on large and permanent storage. In short, internal memory keeps what the CPU needs right now. External memory stores everything else. Each memory chip is made of millions of memory cells, and every cell stores a single bit, either 0 or 1. A single cell has three main control lines. These are a select line, a control line, and a data line. A select line is for choosing which cell to activate. A control line is for deciding between reading or writing, and data line is for sending or receiving the actual bit value. When combined, millions of these cells form the main structure of semiconductor memory. This simple but efficient design is the foundation for all RAM and ROM technologies. And you see the memory cell concept here. All modern memory is built using semiconductor technology. Interestingly, the term RAM is a bit misleading because all semiconductor memory allows random access. RAM can be either dynamic or static. Dynamic RAMs, DRAMs, uses capacitors to store bits, but these capacitors slowly leak charge, so the data must be refreshed constantly. Static RAM, in contrast, use flip-flops. They don't leak, so no refresh is needed. Both RAM types are volatile, but they serve different purposes depending on speed, cost, and size. Here we see the semiconductor memory types and features. We will talk about all of them during the presentation. Dynamic random access memory stores each bit as an electrical charge in a capacitor. A charge capacitor represents 1, while a discharge capacitor represents a 0. However, the stored charge gradually leaks away, so DRAM must refresh thousands of times per second, even while powered. It's simpler and cheaper than SRAM, but slower. That's why it's used as main memory, where the capacity matters more than speed. Here we see the RAM structure. It's not very complicated, as you see. Static random access memory stores data using bit-stable flip-flop circuits. This means it can hold data as long as power is supplied. There is no need for refresh cycles. and it's larger per bit. It's more expensive than dynamic RAM, and it doesn't need refresh circuits, I said, and it's faster, and it uses as cache memory. Structure is more complex, so it's larger and more expensive, but on the other hand, it's much faster. SRAM is primarily used for cache memory, which sits between the CPU and main memory to improve overall performance. Let's compare them directly now. Dynamic RAM uses capacitors, which require refreshing, and these are slower, but they are small and cheap, perfect for main memory. SRAM uses field flip-flops, needs no refresh, and is very fast, but expensive and physically larger, and is ideal for cache memory. The two are complementary. One offers capacity, the other is speed. Now let's move to non-volatile memory. Memory that retains its data even when it's power off, and it's ROM, read-only memory, and it's used for permanent storage for critical softwares. Examples for the RAM: the microprograms, system BIOS, and fixed functions tables or embedded instructions. These memories are essential for system startup and embedded applications. And now you see the ROM family members. These are ROM, PROM, EPROM, EEPROM, and flash memory. And all type of ROMs is used for firmware and embedded systems. And programmable ROM. It's a memory chip on which data can be written only once. The difference between PROM and a ROM is that a PROM is manufactured as blank memory, whereas ROM is programmed during the manufacturing process. Erasable programmable ROM is a type of memory chip that retains its data when its power supply is switched off. Once programmed, an EEPROM can be erased by exposing it to strong ultraviolet light sources. Electrically easily programmable ROM is a type of non-volatile memory used in computers and other electronic devices to store small amounts of data that must be saved when power is removed. These can be programmed and erased in circuit by applying special programming signals. The number of times it could be reprogrammed is limited. And the flash memory is an electronical non-volatile computer storage medium that can be electrically erased and reprogrammed. Flash memory is a specific type of EEPROM where large amounts of static data are stored, such as in a USB flash drives. Today, flash memory is everywhere in USB drives, SSDs, and mobile devices. It's essentially the modern descendant of ROM. In a real computer, memory is built from multiple chips organized together. Each chip may handle only one bit, but combining them allow the system to store complete bytes or words. As you see in this example, 1-bit chips can be combined to form 256 kilobyte memory. This is known as a bit slice organization. In a 1 megabyte memory, several such modules are grouped, and chip select signals determine which chip or module is active. The modular design allows scalability. Memory can be expanded easily by adding more modules. Now let's discuss the memory errors and how they are corrected. Memory faults fall into two categories: hard failures, which are permanent physical defects, as you know, Soft errors, which are random and temporary, for example, caused by an electrical interference or cosmic rays. Soft errors are more common and can cause bit flips in data. To prevent data corruption, systems use error detection and correction codes, such as Hamming code or SEECDET. This is single error correcting, double error detecting. There are three main techniques used in modern memory systems. One is parity bit. It adds one bit to detect single bit errors, but cannot correct them. The popular one is Hamming code. It uses multiple check bits to identify to correct single bit errors. The other, signal error correct, double error correct, and this is an improved Hamming code that detects 2-bit errors and corrects 1-bit errors. And you see the basic error correction code function here. Hamming codes work by adding parity bits at the position that are powers of 2, for example 1, 2, 4, 8, and so on. Each parity bit covers specific data bits, forming a pattern. When a bit is corrupted, the system checks all parity bits and calculates a syndrome value that directly points to the fault bit. The fault bit is then flipped automatically to restore correct data. This makes Hamming code both elegant and efficient. As processor became faster, traditional DRAM became a bottleneck. New DRAM designs were created to synchronize better with CPU timing. Synchronous DRAM, SDRAM, operates in sync with the system clock, allowing the CPU to predict exactly when data will be ready. It also supports burst mode for sequential reads and improving speeds. And you saw the SDRAM scheme here. Rambus DRAM is developed by Rambus Company, uses a high-speed serial bus to deliver data over 1 gigabit per second. Although it offered impressive performance, it was expensive and eventually replaced by the DDR technologies. Double data rate SDRAM takes this further by transferring data twice per clock cycle on both rising and falling edges. This effectively doubles bandwidth without increasing clock frequency. And these features make DDR SDRAM is more preferable. Cache DRAM integrates a small SRAM cache, usually around 16 kilobytes, on the same DRAM chip. This acts as a fast buffer, reducing latency and speeding up block data access. It's a hybrid approach that combines the density of DRAM with the speed of SRAM, actually. To conclude, internal memory forms the backbone of computer and performance. DRAM provides large capacity, SRAM offers high speed, and ROM ensures stability and permanence. Error correcting mechanisms guarantee reliability, and advanced DRAM types like SDRAM and DDR continue to evolve to meet the CPU performance demands. In short, internal memory is not just a storage component, it's a critical, dynamic system that balances speed, size, cost, and reliability. Thank you, friends.